Here are the understandings from the guide. The first understanding is kinetic energy. Well, what is kinetic energy? It's energy due to an object's motion. And the formula, which I believe you're given in the data booklet, is a half mv squared. Now, kinetic energy might seem simplified as K dot E or capital E with a little subscript K. They're both two ways of defining or symbolizing kinetic energy. So if an object has a mass and a velocity, it will have some kinetic energy. However, what is gravitational potential energy? If we have an object in a gravitational field G, and the object has some mass m, then relative to some base height, if we've had to, for example, raise the mass a certain height h in this field, the mass possesses gravitational potential energy worth mgh. M is the mass in kilos, g is acceleration due to gravity, and h is the height above a base level, or the ground most commonly. What is then elastic potential energy? Before we go on to elastic potential energy, gravitational energy is sometimes simplified to EP. Elastic potential energy, which in the guide is also called EP, rather confusingly, is a half times K, which is the spring constant, times X, which is the extension squared. Because when we have a spring, which is basically a coil of metal, when it's at rest, it has an equilibrium length. Springs are defined by their spring constant K, whereas if I extend it X meters, then the spring will contain some elastic potential energy, and that's what EP is. In fact, we can derive the elastic potential energy from the force time graph, because there's a concept of work, and the work done is the same as the energy we've transferred to the system. Work is given the symbol W, and it's the same as the force times by the displacement in the direction of the force. So we have to have this cosine theta there. But if we were to have the force distance graph, force distance, in this case, in the case of the spring, the distance is the extension x, then we end up with a straight line, because Hooke's law tells us that force is equal to the spring constant times by the displacement. Now, if work done is the force times by the displacement, the meaning of or how we would interpret the force distance graph is that the area beneath the force distance graph is the same as the work done. So the area under a force displacement graph is the work done, and in this case it's just a triangle through geometry. So for this would be work done, or the change in energy, is going to be a half times the base x times by the force, and since force from Hooke's law is k times x, we get that the work done, or the change in elastic potential energy of the spring, is equal to a half times kx squared, which is where this thing comes about here. Then we need to define what power is. Well, power is defined, or we have to understand power as the rate of energy transfer. when we ever talk about a rate of something, it's how something changes with time. So it's the rate of energy change per unit time, and the unit is the watt or joules per second. And since power is the change in energy divided by time, it's also the work done per unit time. Let's just tidy it up a bit. Delta for the Greek letter delta, which simplifies a change in, delta E over delta T, or W for work over delta T. Next, you have to understand what we mean by the principle of conservation of energy, and that's a very important principle which underlies a lot of physics and comes up in many topics, and that is that we can the principle of conservation of energy is that neither energy can either be created nor destroyed, but can only be transferred from one type to the next. So a simple example of that is if I hold the mass up in a gravitational field, it has gravitational potential energy. As soon as I release that, it will fall towards the ground, and the gravitational potential energy will be converted into kinetic energy through the principle of conservation of energy. But we still, if we were to add up all the energy before and add up all the energy after, then through the conservation of energy principle, they should equal. However, many systems are not efficient, which means that a lot of the energy is wasted in some senses to thermal energy, and the concept of efficiency is defined as the useful energy that we get out divided by the total energy in, and this is important in machines. For example, we want to make things more efficient. We don't want to lose energy most of the time. And since power is the rate of change of energy, we could also write this as the power out divided by the power in. Since power is the rate of change of time, the times cancel, if you like. So that was a brief summary on work, energy, and power.